All right, welcome back. It's my big pleasure to introduce you to Merve Bodur. It's not an understatement to say that she's one of the stars nowadays in all the optimization fields. Involved in several communities, computing society, optimization society, and her work is absolutely breakthrough. And it's so happy to hear that she's also working on decision diagrams. So Merve did her PhD from the University of Wisconsin, Madison. Then she did a postdoc later at Georgia Tech Institute of Technology, and now she's at the University of Toronto teaching us. And please, Merve, take it away.
Thank you so very much, Andre, for this very, very kind introduction and some overstatements. Yeah, thank you so very much, Andre and David, for in the first place for organizing this amazing winter school. And I do hope that the recordings will be, for many talks, will be available, because I think this will teach our community, especially the new generation, a lot about decision diagrams and advance this exciting research area much more. So yeah, today it's my great pleasure to talk about this recent work with my PhD student Moira McNeil on this BDD-based approaches for a special, actually two special classes of, if you will, two-stage stochastic programs. So my main area has been stochastic programming. So we wanted to do something a little bit with the BDDs, which is super exciting to us. Moira and I have been always very much excited about them. So we decided to hopefully leverage a little bit of these BDD structure, especially this network flow formulations that Margarita has luckily introduced for me in the previous talk on these decomposition types of algorithms for two-stage stochastic programs. But I just want to mention one more time that all the credit goes to Moira here. I'm just here as the face to present her work. Okay, so here's the outline of today's talk. By the way, feel free to interrupt me at any time. I think we have plenty of time, so I will be happy if you interrupt me and ask your questions, or if you have any comments during the talk. Also, feel free to just unmute and speak, or if you feel more comfortable, also you can post your thoughts, questions on the chat screen. I will try to keep an eye on that as well. All right, so here's the outline of today's talk. So I will have a quick introduction about two-stage stochastic programming, and then introduce one special class of two-stage stochastic programs from the literature, which we do have a slight extension in this work. And we have another special class of two-stage stochastic programs that I will introduce next. And then I will tell you a little bit about the decomposition algorithms. Thanks to the use of decision diagrams, they will all boil down to Bander's decomposition types of algorithms. I will present those. And then we care about, as the stochastic programmers, we also care about sometimes this risk-averse type of decision making. In that regard, we will incorporate a particular risk measure, conditional value at risk, into our stochastic programs. And this whole decomposition frameworks that we'll talk about will nicely go through. And then I will present you some experimental results. And I will explain shortly, but I will be using a particular stochastic variant of a graph theory problem as our running example. And our experimental results will be also for that graph theory related problem, combinatorial optimization problem. All right, so let's start it with this generic form of two-stage stochastic programs. So here what we have is this: we are trying to, of course, we do have two-stage stochastic programs, which means we get to make decisions two times in time. So our first stage decisions will be denoted by the x's, and then in our problem, we will like to, as a decision maker, incorporate uncertainty in certain problem parameters. This set of random variables, the vector of random variables, will be denoted with this calligraphic omega. And then after we will make our first stage decisions x's without knowing the actual observations of our random variables represented with this vector omega. And after we commit to our first stage decisions x's, then these observations of the random variables will be revealed to us in one shot altogether. And then accordingly, we will get to make a secondary set of decisions denoted with y's. But since this second stage decisions, also known as this recourse decisions, they are called recourse because if you made any mistakes in the first stage, you will have a second chance to fix your mistakes from that first stage. So these recourse second stage decisions wise, they will of course depend on the random observations, which we will denote shortly as the scenario. So depending upon how the future unfolds, you will be getting to make this secondary set of omega types of decisions. So what is the objective? We will be starting with this risk-neutral approach. So this is the most commonly used form of stochastic two-stage stochastic or general stochastic programs, where we are trying to find our primary implementable decisions x's. And x's here should come from this feasible set for simplicity now, we are assuming that everything is linear. So our X decisions should satisfy a set of linear inequalities. And in terms of the types of X decisions, you might have some binary variables, some general integer variables, and some continuous variables. So we allow mixed integer X decisions, but I split them into these three sets, binary, integer, and continuous, because they will come into play while we are talking about these special clauses of two-stage stochastic programs. So we are trying to find our deterministic X type of decisions in order to minimize their immediate costs, plus this cost associated with the second stage, with the future, if you will. And in a risk neutral setting, we are trying to optimize the expected total cost. So the future cost, which depends on our random vector represented by omega, because at every future path, we might be making different sets of decisions and accordingly incurring a different set of costs. And we will make this well defined by adding this expected value operator. So we are trying to find our, again, X decisions to optimize the immediate cost of the first stage decisions plus the cost from the second stage from the future. And this future cost is represented by this function calligraphy Q, which is parameterized by our first stage decisions plus whichever scenario, whichever uncertain realization we observe in the future before we move on to the second stage. So this Q function is called the value function or the recourse value function, and it tells you how much cost you should expect from the second stage decisions. Given your first stage decisions, X's are being fixed, then this will of course parameterize the feasible region of the second stage. What type of second stage decisions under that omega scenario, omega we can take. Of course, it will depend on what scenario occurred and what type of decisions we already committed. And in terms of the cost, we could also very well have some uncertainty in the cost coefficients. And here again, I will be assuming for simplicity, everything is linear in terms of the constraints, except potentially some integrality restrictions on the decision variables. So this is the general form of a two-stage stochastic program. So moving forward in this talk, we will be focusing our this special class of two-stage stochastic programs where the recourse decisions are all assumed to be binary. So all of our, under every scenario, the whole set of decisions that we will consider, they are going to be always binary. Of course, this will give you the idea already, a spoiler alert for these audiences. This will be because we would like to use binary decision diagrams. But if you would like to be a little bit more careful, you can potentially allow some other types of recourse decisions if you don't need them in the BDD, or if you are going to, for instance, build multivariate decision diagrams, maybe it will be okay to consider extensions of our ideas for the general integer, bounded integer cases. But for moving forward, I will assume that we have purely binary recourse. All of our second stage decisions are binary. Okay. And I have a couple more other assumptions moving forward to simplify our jobs. And these are pretty standard assumptions in stochastic programming. First of which is this so-called relatively complete recourse assumption, which ensures feasibility of our problem. So what does it mean more explicitly? For any feasible first stage decision vector X, if you give me any X from this calligraphic feasible set X, then for that fixed X, whichever scenario omega occurs, then I will always be able to find a feasible set of second stage decisions. So I ensure feasibility. As long as you choose something feasible in the first stage, you will remain feasible for whatever scenario occurs in the second stage. So this is called the relatively complete recourse assumption. And it is very, very easy to satisfy by means of some modeling tricks. So it's a reasonable assumption in practice as well. The second assumption that we will have is this finitely many scenarios for the future uncertainty. So there could again be many ways to model uncertainty, but we are considering this particular form of stochastic model where uncertainty is represented by a finite set of scenarios. Again, scenario will be denoted by omega. It will be the index for the scenario, and the full set of scenarios, which is going to be this finite set capital omega. All right, so basically this is the generic form that we will consider, but I will now specify some even subclasses of this stochastic programs with binary recourse. All right, so starting with this special class of two-stage stochastic programs from the literature, I believe Leo is here. So I will be actually referencing this work by Leo and Cole from 2018 quite a bit, because we got the first inspiration from this work, and we do have, first of all, a small extension of this work and another special class that I will introduce shortly. So that's why let me first tell you guys, if you haven't seen this amazing work by Leo and Cole, what they consider as a two-stage stochastic programs. So in terms of the first stage, everything is exactly the same as I introduced before, but regarding the recourse problem, this second stage problem, they consider a special structure. So in terms of the decisions, they are still purely binary. All the recourse decisions under a scenario, they are all binary. And these constraints just telling you, you have a bunch of just scenario related constraints. Okay. The second thing, and this is the key restriction as a special cause of two-stage stochastic program, is the first set of pin constraints. So they assume this special structure where you will be adding for every possible, or for some of at least these binary variables from the first stage. So I goes from 1 to n and 1, which means we are only linking the some binary decisions from the first stage to the second stage. And we are actually linking them one variable at a time to the second stage. So if you have a binary variable xi from the first stage, if that takes the value 1, then you would like to enforce an additional set of constraints on that scenario's problem. So that's the special structure they consider. And their main idea for this special type of two-stage stochastic programs is as follows. So for every scenario omega, they will consider this scenario problem. And this is a pure binary program for which they will create a binary decision diagram. And assuming that how they will start creating diagram is they will assume that all these linking type of binary variables from the first stage, they are taking the value 1. In other words, they are taking all the possible constraints for this model. So they consider everything, all the enforced constraints, thanks to these first stage links, and they build a binary decision diagram for this subset. And then, in order to incorporate this first stage decisions, turning on or off these additional constraints, they do incorporate some arc capacities on these BDDs that they built for scenarios. So we built one BDD per scenario, but there will be some arc capacities parameterized by these first stage variables that will be able to encapsulate what we see in this two-stage stochastic program structure. And once they do that, I will, by the way, explain the details shortly about this approach. And thanks to this approach, now that you have a BDD, thanks to this, and this X's, the links from the first stage only happen to be as just simple arc capacities on the BDDs, you are able to convexify this whole second stage subproblems through decision diagrams. And once you do that, we know, as Margareta, for instance, told us, you could immediately go to the flow formulation for these decision diagrams, but now arc capacities will just come as this additional constraints on the flow variables. But no matter what, you have this nice linear program or flow formulation there, which will allow us to use standard Bander's decomposition. So we don't have to now worry about the binary restrictions of our second stage variables. Thanks to this BDD trick, everything is convexified. So we live in a nice region through which we can obtain the standard Bander's cuts and employ a Bander's decomposition algorithm. So that was the key idea from Leo and Paul. So I just want to have this one slide that summarizes the other types of works that we use where decision diagrams have been used for stochastic optimization. First of which is this paper from 2017, where they do consider a different type of uncertainty, namely endogenous decision-dependent uncertainty. In our work, we are sticking into exogenous uncertainty. So for this work by House et al., they consider this endogenous uncertainty where their decisions, first stage decisions, they do change the probabilities associated with the scenarios. And what they do with the BDDs is they construct a set of binary decision diagrams that will be able to help them efficiently characterize these probabilities, scenario probabilities, as a decision-dependent objects. And once they do that, they end up with for the whole problem, they end up with a mixed integer programming reformulation that can be solved by means of commercial solvers, for instance. So for more recent work is by Tiago and his colleagues, where they considered this particular scheduling problem and last mile delivery type of a problem, for which they propose a two-stage stochastic programming formulation. And then for that two-stage stochastic program, what they did is they employed the decision diagrams for both first and second stages. And after they built their diagrams, they linked them through these channeling type of assignment constraints, which yield this big large-scale integer program, and they solve it directly. They don't employ decomposition, but thanks to this strong, tight formulation of this IP, they were able to get good quality solutions relatively efficiently compared to the existing approaches. And finally, Margareta has just presented her cool work from 2021, where they proposed this BDD-based combinatorial cut and lift project type of a procedure, and they have one application in their paper on a particular norm normalized type of a chance constraint problems. So it also falls into the stochastic optimization. So I would say like the literature on the use of decision diagrams for stochastic optimization, in particular stochastic programming, has been still quite rare. So we are hoping to inspire many of you to contribute to the stochastic optimization literature with the use of decision diagrams. All right, so going back to my special classes of two-stage stochastic programs. So here we started with this general first stage problem, and the key will be in creating these special classes of our two-stage stochastic programs is how to specify this recourse value function Q. So this is what we had seen from the literature, the Leo's approach, where this individual binary variables from the first stage, they will activate a set of constraints for the scenario problems, which are purely binary, by the way. So our first idea is a simple generalization of this structure from the literature, where instead of using these individual xi variables as the indicators to turn on bunch of constraints for the second stage problems, we generalize this and then we say, actually, it's okay to put any other expression here that will allows you to enforce this additional set of constraints. So we don't need to do this one variable at a time. It could be a little bit more general than that. And how general it is, for instance, one generalization that we have here, this I is the indicator function. If the logical expression denoted by this L thing, if the logical expression given to this indicator, it is true, then it returns 1, in which case we enforce these additional set of constraints for our second stage problems. So what we say is that as long as you have any logical expression there, for instance, I can have something like for this L object here, let's say rather than a single binary variable, but I can say if x1 is equal to 1 and if x3 is equal to 0 or x4 is equal to 1, I can have this type of a logical expression. If this is true, then I will enforce my constraints. Again, these logical things might come from your particular applications, or it might be something like even something more general. You have a general type of constraint. If this constraint holds, then I would like to enforce a set of constraints in my scenario problem. So you can have anything that you can think of there as the logical thing, which will be indicated by the indicator function, as long as, so you can actually model this relationship, this logical relationship. And in our applications, I will show you shortly, we don't need to introduce any more decision variables to be able to implement this logical things. We can directly use our existing X variables to be able to model this relationship. But if you consider something more general, you might need to define some other scenario dependent. For instance, I guess I'm not using Z of omega type of variables, maybe to be able to do this bridge type of a trick to implement this logical conditions. But for us, again, for the problem that we consider, we got lucky that we don't need to introduce any additional variables to be able to handle this generalized case of logical relationships. Okay, so this is the first type of a contribution that we have. And the second thing is a little bit more, I guess, different than what we've seen in the literature, is what we are calling this decision-dependent, special type of a decision-dependent cost structure in our stochastic program. So what do we have here? We again have, as usual, the pure binary recourse and bunch of constraints associated with the scenarios. We have nothing to do with them. And in this case, these W's also, they have nothing to do with the first stage variables X's. But the key here in this new special class that we consider is this purple things, where again, you might have any type of logic. And if this logic holds, then we have here this D vector, which is whose components I'm denoting with I, for the cost vector here for our recourse decisions. If this logical thing is satisfied, then we would like to make the cost of that ith component of the decision variable 0. So if you did something in the first stage, which is a function of the x's here, and there is this logic that is satisfied thanks to these x decisions that you made in the first stage, that brings you this cost of 0 for certain actions in the second stage. So I will show you some applications, some motivational examples for this, but it's almost like you commit to something in the first stage, and then in the second stage, certain options, certain decisions comes for free for you. Okay, so this is the second class that we will be considering. And moving forward, for us, as a quick reference, I will be always denoting these two approaches as number 1, which is related to literature, and number 2 is a little bit different than what we've seen in the literature. Okay, so just to tell you a little bit of like motivations and maybe some applications behind these special classes of two-stage stochastic programs. For the first approach, the main idea is you need to satisfy certain requirements either in the first stage or in the second stage. If you have this type of a condition, it is usually amenable to this setting one. The second one, as I just actually mentioned, is more amenable to these type of cases where you make some investments. Let's say you invest in an item in the first stage, then in the second stage, it comes at no cost. As in, like, you are maybe buying some contracts, or you are buying some items, you are reserving something, which makes this use of these items at no cost in the second stage. So I'm not going to get too much into details because I will already give you a novel application where I will use all of these, I will illustrate all of these ideas, but just to name a couple more than what we will actually focus on moving forward, here are a bunch of, again, combinatorial problems. Their stochastic versions might be amenable for these, one of these, or both of these two settings. For instance, let me start with the stochastic vertex cover, where you are given a graph and you are trying to choose a set of vertices that will cover all the edges, that will touch all the edges. So for this vertex cover problem in the stochastic version, you might need to choose a set of vertices in the first stage, but then you will complement it with additional selection of vertices in the second stage. And as a whole, your combination of first and second stage decisions should lead to a vertex cover. So in that case, if we consider the first approach, then if you make some decisions about vertex selection in the first stage, but there is this edge that is not covered in the first stage, then your second stage decisions, they are now more restricted because you need to choose more vertices in the second stage to be able to cover any uncovered edge from the second stage. In other words, the main condition here is what I'll be referring to here is each edge should be covered either by in the first stage or in the second stage. That's the setting that this will fit into. On the other hand, if you want to interpret the same problem from our secondary approach, then you can interpret it as follows. If you have selected a vertex in the first stage, then you are allowed to select it again in the second stage, but this time it comes at no cost. You can choose it for free, and all the edges that it is touching, all of its incident edges, will be already covered for you for free in the second stage. So you can do the same type of analogies for a bin packing problem or stable set problem, but my running example will be actually, I will talk to you about the contribution shortly, this dominating set problem in the, again, graph-related combinatorial problem. So I will actually show you both of these approaches on this particular problem. Before that, let me just quickly summarize our contributions. So in this work, what we are doing is, first of all, we are starting with this approach by Leo and Cole, and we are generalizing it a little bit, and we are using this BDD-based decomposition approach for this generalized special class of two-stage stochastic programs. And this is our approach one. And we also propose this secondary approach. And again, it will be, we will show shortly that it will be amenable for this BDD-based decomposition approach. So this is our second thing. And both of these approaches could also be extended to a risk-averse setting. And in that regard, we will be incorporating a particular risk measure called CVAR. So, and then we will see that our decomposition, BDD-based decomposition approaches will simply go through when you add this risk-averse component to your stochastic program. So, and then this is another contribution, because this actually, to the best of our knowledge, this constitutes the very first decomposition method for two-stage stochastic programs with binary recourse and CVAR in them. And I will also explain this in more detail in the upcoming parts. And finally, we apply all of these methodologies, ideas that we come up with to a specific problem, namely a minimum weight dominating set problem, for which we first actually propose a stochastic variant, which is itself novel, and then we illustrate our generic decomposition ideas on the stochastic variant of this minimum weight dominating set problem. Okay, so now let me explain our running example, this novel application. So let's start with this deterministic version, which is this minimum weight dominating set problem, which is defined on a graph. So we are given a graph, a set of nodes and a set of edges, and it's an undirected graph. And the numbers that you see adjacent to the nodes, they are corresponding to weights of the nodes. And what is the dominating set? A dominating set is a subset of the vertices who's actually touching every other vertex. So if, for instance, you choose a vertex, let's say V0, then this vertex definitely dominates itself, but also its neighbors. So if you choose V0, then it will also dominate anybody else that it touches, anybody else that it is adjacent to. And the goal is to choose a subset of the vertices that will dominate everybody in the graph. So here's a quick example. So V0 and V2 is indeed a dominating set because it is actually able to dominate. They are able to dominate everybody else, including themselves in the graph. So this constitutes a dominating set. Among all feasible dominating set objects, which one we are looking for is the one whose total weight is the minimum. And in that regard, the weight of this dominating set, namely 7, it is indeed, for this simple example, it is the minimum possible one. So please feel free to interrupt me if anything is not clear. Otherwise, I will move on with the extension of this minimum weight dominating set problem. So this problem itself, it has a bunch of applications. The most common one I would say is this sensor location type of problem. So you can think of these nodes as certain locations, certain regions. And when you place a sensor, let's say at this location, the edges indicate whether some other areas like these neighboring areas could be actually covered by the sensor placed at that location V0. And your goal is to place the minimum cost sensors at certain nodes to cover all possible areas. Another application, which is maybe a little bit more interesting at the current times, is this disease suppression and control type of an example. There are also some routing examples or even some examples from public goods in networks, but all, of course, as you can imagine, some network examples. Okay, so what do we do in particular in this work is we first extend this problem into a stochastic setting. So what do we have in the stochastic extension? So we consider two things as being potentially stochastic. One is vertex existence. So some vertex might fail actually in our graph. Second one is these weights that are associated with the nodes of our graph, they could very well be uncertain as well. So here's on the top, I do have the original given graph with the original weights and all the nodes exist in the original graph. But then there will be these finitely many scenarios. Let's say for scenario 1, scenario 2, and scenario 3, our graph will potentially look better because, for instance, under scenario 1, this node V0 will actually fail. It's not going to exist. So we cannot choose this, or even if we choose it, it's useless. We don't need to cover it, dominate it. Neither its selection will not give us anything. So we don't even have to bother considering this node V0 under scenario 1. Moreover, of course, weights of these objects might very well also change. For instance, the weight of V3 here was 5, but under scenario 2, it is increased to 10. So some vertices will potentially fail under scenarios, as well as potentially the weights of the vertices will be updated, modified for different scenarios. So we will have different scenario instances as the graph. Right. So I believe Mohsen has a question.
Yeah, thank you. So you do not bound the number of vertices that could fail, right?
Not necessarily, but of course, in the data generation, you might want to factor that in so that you end up with some reasonable instances. Because, I mean, in theory, every vertex could fail, right? But the probability of all of them failing simultaneously will be pretty small. So you may not want to maybe consider that as a potential scenario. But it depends on the historical data that you have. It will be how you model uncertainty underlying stochastic process in terms of vertex failures.
Yeah. And what about edge failure?
It could also be, if you like, incorporated, but we do not consider edge failures in this work. So mostly our inspiration was when we looked at the literature of dominating set, minimum dominating set, we see some stochastics works individually just considering vertex failures, and some works were considering uncertain weights, and we combine them. So we are the first work considering both simultaneously. But of course, like if you would like to, you could very well also consider edge failures. It's not going to change anything in the framework. It's just now some other edges will not exist in this scenario graphs.
Okay, thank you.
You're welcome. So yeah, in terms of the ideas, methodologies, nothing will change if edges also fail. But if you have also edge failures, it means you will have many more random variables in the graphs in your problem, which will include the need of how many scenarios like you need to use to represent the underlying uncertainty well. So it will just increase your need of scenarios, I will argue. Okay, there are no more questions. Let's move on. Okay, so this will be our running example. I will explain our specific ideas on this dominating set, stochastic dominating set problem, and also the computational results will be in regards to this example problem. All right, so assume I do have, I actually forgot to mention what is the actual problem. Maybe let me just tell you one more time for completeness. What is the first stage and second stage decisions and our objective in this problem? So maybe let me clean this up. So what we are trying to do in this problem is we will get to make decisions 2 times because we are considering 2-stage stochastic program. We will first, in the first stage, choose a subset of the vertices, as many as you want. Of course, they will come with their associated cost. And in the second stage, we will get to choose another set of vertices with their, again, associated scenario cost. And our goal will be to minimize the expected total cost of our vertex selection. In other words, the total weight that we will incur by this vertices selected in the first stage as well as the second stage, subject to at the end of the second stage. So when we combine the vertices selected both in the first and the second stages, then that combined solution should constitute a dominating set. So everybody that exists, every vertex that exists in the scenario graph, they should be for every scenario, they should be dominated, they should be, in other words, covered. So here's a quick example. For instance, I'm not going to be able to necessarily find the optimal solution, but let's say in the first stage, I will choose this node V0. And then when I move to the second stage, if the node exists, it will be already there because I already selected it in the first stage. But if you look at, for instance, scenario 1 problem, then the selection of this V0 from the first stage will only be covering V0 itself and its neighbors, V1, V3 doesn't even exist. So among these remaining nodes, V2 and V4, I still need to choose at least one to cover them. Let's say maybe optimally, then I will get to choose V2. So this will be my choice in the second stage. So if you move on to scenario 2, then the selection of V0 will help you to dominate V0, V1, and V3. But again, among the remaining ones, based on the cost, let's say I will choose again V0. And if you go to the third scenario, now the selection of V0 in the first stage, it means nothing because that node failed in the second stage. From the remaining nodes, in order to obtain a dominating set for the remaining graph, I need to choose, of course, V1. It has no neighbors. And let's say I need to choose V3, which will cover V3 and V4. So this will be an example feasible solution to the stochastic variant of the dominating set problem. Is it the optimal? I don't know, probably not. Okay, so now that we have this stochastic variant of the dominating set problem, how can we solve it? It's the standard 2-stage stochastic programming model, and the most natural approach, the first thing that can come to your mind is, if you are familiar with stochastic programming, is you can combine these 2 stages and create this large scale, what we call the deterministic equivalent problem, which is technically a large scale, in this case, binary program. So you can create this big, large scale binary program where you will have these scenario copies of the second stage decisions. So it will be a large scale, but it's an integer program that you can give to your favorite solver, Cplex or Groby, and hope to solve it. But unfortunately, if the number of scenarios that you have, it gets larger, this problem, unfortunately, is going to get hopeless. So it doesn't scale well at all with the number of scenarios. And for certain graphs of size, let's say above 50, the need for scenarios, the sample size will be actually in such a way that we won't be able to even afford to solve this problem by means of this deterministic equivalence. So it's not an option. So, but again, if you're familiar with stochastic programming, it does have stochastic programs. They do have this very special structure called this block diagonal structure. And it usually, that's why leads to these decomposition types of algorithms where you will decompose for scenario, the recourse stage, you will decompose it by scenario. And if you would like to leverage this, the most natural approach from the literature will be the use of this so-called integer L-shaped method. So it's a decomposition algorithm which will decompose your whole problem into a master problem and bunch of sub-problems, one per scenario. Let's say omega. And you will create this loop. Master problem will give you a candidate solution that you will pass to the sub-problems. It will decompose by scenario. You will solve each one of these sub-problems, according to which you will be returning some cuts to your master problem. And in this approach, in this integer L-shaped method, the difficulty will be these sub-problems, you need to solve them as binary programs, again, because we have binary recourse. So here's a quick table. For instance, for some arbitrary choice of these dominating set, stochastic dominating set problem for graphs of sizes 30 nodes, 40 nodes, and 50 nodes, if you try to employ this integer L-shaped method, although it's a decomposition method and it does much better than this first pure binary program approach, this decomposition works a little bit better, but as you can see in terms of the times, again, it does not scale well. When you hit 50 nodes, you are already hitting our time limit of 1 hour. So it's getting still harder to solve for larger scale instances. So it's not enough for this problem class on its own. So our idea is to hopefully leverage the use of decision diagrams to come up with a more successful decomposition algorithm. All right, so here's the integer L-shaped method. I already explained it in the previous slide, but you decompose the problem into a master problem and a sub-problem which decomposes by scenario. And at every iteration, you will be solving your master problem, which will give you a candidate solution that you will pass to your scenario sub-problem, for which you need to employ an integer programming type of approach. You need to solve them as a binary program. And then what is this dual solution? This is not actually, sorry, it's a typo. You need to get the solution of the sub-problem solutions you need to get to be able to generate these so-called integer L-shaped cuts. And then you repeat this loop until you find no more violated cuts. So what we propose in this work is very similar to the decomposition approach from the literature, thanks to Dave and Cole, is we are first of all starting to create one decision diagram, one BDD per scenario. And we store them, we create them once and for all, and then we will use them all along. And again, it's a decomposition algorithm, which we will start with solving the master problem, which will give us a candidate solution. And then this time our sub-problems, one per scenario, because we have BDD representations for them, they could be efficiently solved by means of a shortest path algorithm. And more importantly, because these guys are now, they are becoming a linear programs, you have this flow formulation. After you run the shortest path algorithm, efficiently you can inquire their dual solutions of this LP, using which you can generate standard, I would say, Bander's cut. So here we do have integer L-shaped cuts. On the right-hand side, we have traditional pure Bander's cut, which will help us to get them faster, and as well as they are going to be stronger. So this is what we will have, but in terms of what we employ more specifically on the right-hand side, depending upon the special classes of two-stage stochastic programs, we will have some differentiation. Okay, so let me remind you again this first approach, which is a simple extension of the method from Lozano and Smith from 2018. What was this approach? Number one is, if based on your first stage X decisions, if a logical condition is satisfied, then you would like to enforce an additional set of constraints for your second stage problems, scenario problems. And for each scenario, we will be building one BDD. Okay, so how does it translate to our stochastic minimum weight dominating set problem? So it's as simple as follows. So if you have made your first stage decisions X's, but there is a vertex V that is not dominated in the first stage, then whatever you choose in the second stage, you need to dominate such vertex that hasn't been dominated in the first stage. Because again, the combination of our first and second stage decisions, they should constitute the dominating set, which means every node V must be covered. As such, if it hasn't been covered in the first stage, it needs to be covered in this dominated in the second stage. So in terms of this logical thing, our logical condition looks like this here. So if a vertex V is not selected, so if XV is 0, nor one of its neighbors has not been selected either. So this N prime is for a given vertex V here, it is corresponding to its neighborhood excluding itself. So in this example, V has these two neighbors, U2 and U3. So in this example, if V is not selected, nor U2 or U3, then it means V has not been covered in the first stage, which means in the second stage with our recurse Y decisions under each scenario, it needs to be covered. So either in the second stage, this V needs to be selected, or one of its neighbors needs to be selected in the second stage. So with this logic in mind, let's try to build our decision diagram. So here's a full original graph, dominating set graph example, but let's consider what happens under one scenario. So we will build one, let's say this is our scenario 1 graph where node 2, V2 failed, and some edge weight, vertex weights probably modified. And for this scenario, for each scenario, we will be building a decision diagram. Let's build it. So how we build this decision diagram is, first of all, we assume that nothing has been selected in the first stage in such a way that you are enforcing all possible domination constraints of the second stage. So everybody has to be covered by purely your choices in the second stage. You start with this X hat equal to 0. You didn't choose anybody in the first stage. And you build a decision diagram for this scenario graph for that case that the first stage decisions has been used for you. So we built the decision diagram by using the standard state definition, which are the vertices that are not dominated, that are still in need to be dominated. So in this graph, the node 2 doesn't exist. So we start with nodes indexed by 0, 1, 3, 4. And then now let's build the diagram. If you decided to choose this vertex V0, then you actually covered, if you choose V0, then it covers, dominates itself as well as its neighbors. The only guy that is not dominated remains as this node 4. On the other hand, if you haven't selected V0 indicated by the stashed arc, then everybody still need to be covered. Okay, so now things will get a little bit interesting, because if you now on top of V0, you haven't selected node V1 either, we are going to end up being infeasible. So as you can see, if I haven't selected V0 nor V1, then I will end up being infeasible, because some nodes now, in particular in this case, V1 has no more option to be dominated because it's not selected itself, and its only neighbor V0 has not been selected either. So in that case, this node V1 will be our, what I will call our source of infeasibility. So at this node, we end up with this V1, which hasn't been, unfortunately, which has no more options for the upcoming decisions in our decision diagram to be covered, to be dominated. As such, we are going to end up being infeasible here. But there's a good thing that we can recover from this infeasibility by getting help from our first stage decisions. So if you look at this V1, had you selected V1 or its only neighbor V0 in the first stage, then V1 would have been dominated, so the V wouldn't be infeasible. It will be okay, we can just move forward. So that's why, with this in mind, what we are doing is we are putting this V1, which is the source of infeasibility, this node, combined with its neighbors here, namely in this case 0, node 0, their first stage decisions as the arc capacities. Because if one of them are selected, if none of them is selected, then the arc capacity will be 0, and you cannot go through this arc, which will lead to infeasibility. But if any one of them is selected in the first stage, you are still feasible because V1 is now, it's already dominated. So with this logic, you complete the decision diagram. One interesting example that occurs, for instance, after this node here, if you are ended up with, if you still have on your list V3 and V4 to be dominated, but unfortunately you didn't select your node V4, then both of them will remain not dominated. And how can you fix this? Is for the node V3, V4 here, which is the first source of infeasibility, you need to choose either itself or its neighbor X3 in the first stage. And the other choice of source of infeasibility here, V3, you need to choose either itself or it's one of its neighbors in the first stage to be able to make this feasible path. So there could be multiple arc capacities rather than just one. Okay. So, and one last comment before I move on this diagram is, as you can see, this diagram is relatively large because this different capacities, for instance, if you look at the last layer, unfortunately, because they are different capacities, they prevent us to have more merges. So that's why actually this approach will lead to relatively larger diagrams, because arc capacities are now making these relatively, previously like what we were calling identical arcs, now non-identical. So we cannot merge any further. Okay, so, but one way or another, you build these diagrams, then you can just build this, what Margaret already introduced, this flow type of a network flow formulation for this, where now for these arcs, depending upon what we put on the arcs there as capacities, you will end up with these arc capacities. And you can solve this primal version by a shortest path algorithm. And then we know that it has its dual, and you can take the dual. And the cool thing is our first stage decisions only appear in the objective of this dual problem, which allows us to generate traditional standard Bander's cuts from the dual. So we can do that. And this is actually similar to what Leo and Cole have been done in the past in terms of the generation of the cuts. Plus, we can actually also borrow their cut strengthening ideas in this approach easily. Okay, the second approach now is, again, we will be building one decision diagram per scenario. But what I said is, if a logic holds in the first stage, then we will this time be modifying the second stage cost of our vertex selection decisions. So more specifically for the dominating set, what we have here is, if a vertex V is selected in the first stage, we allow it to be selected again in the second stage, but this time for free. So if a vertex V is selected in the first stage, we are going to reduce its cost to be 0 for the second stage selection. So if we now build our decision diagram for this, let's say scenario 1 graph, with this idea of modification of the cost, the states are exactly the same, and we start again like we done nothing in the first stage and build a decision diagram with all the nodes to be dominated in the second stage. This time, because we don't have these arc capacities, our obtained diagram is actually much smaller than the previous one that we've seen, because we can do many more merges now. And then we put the arc costs. And in this case, the general formula is if you selected a node in the first stage, then it will give you the 0 cost. For instance, for this first arc, if I selected node 0 in the first stage, it will make this whole cost 0. For this one arc, its cost will be reduced to 0. And similarly, you put all the remaining decision-dependent arc cost there. So if you build the diagram in this way, let's go back to, again, it is flow formulation. But now, as you can see, we have some cost parameterized by our first stage X decisions from the first stage. So if you try to attempt to take the dual of this approach, then we will run into an issue, because the dual feasible region is now parameterized our first stage decisions. As such, we cannot use pure standard bandit decomposition algorithm. So, but this is not a stopping point for us. We can actually propose a different type of a optimization problem. And we prove that this first problem, which we have an issue where this parameterization of the first stage appears in the feasible region, it can be pushed to the objective with the addition of these new variables z's, and some z's also appear here. In short, I'm not going to have time. I will not have time to explain in detail, but we can reformulate this first dual by the second dual, which now has the first stage decision only in the in the objective function. As such, we can use pure bandit decomposition algorithm. And again, you can also apply cut strengthening ideas from the paper from the literature. So I will not have time to get into details, but very quickly, as a proof of sketch, what I want to show you is, so this is the relationship that we wanted to show equivalence for, but we don't show this directly from these duals, but we rather go to the dual of this green problem, and we prove that these first primal and the second primals are equivalent to each other, which imply the equivalence for their duals. And in terms of these primals, this on the right-hand side is the standard network flow formulation, where we do have these decision-dependent costs in the objective. In the second primal that we came up with, there is this augmented type of what we are calling flow constraints, because each one arc now, in addition to its standard flow variable, they also have the secondary flow variables, gammas, and they are all getting this additions there. But anyway, so we show that if you get a solution from the first primal, we can construct a feasible solution to the second one with the same objective, vice versa, which implies the equivalence. So to put them all together now, what do we have? We have these two options, where in the first one, which is an extension of Leo's work from the literature, we have these arc capacities on the BDDs are actually depending upon our first stage decisions. Our second approach, where we just parameterize the arc costs with our second stage decisions. So states are exactly the same in both approaches in regards to how we built the decision diagram. Arc capacities in approach one are for each node, the node and its neighborhood that comes as an arc capacity. On the other approach, we are not touching the arc capacities for the flow variables. On the second version, for the arc costs are now in the second approach, arc costs are parameterized by our first stage decisions. We don't touch them in the first approach. And for both, we are building one decision diagram per scenario. And as I mentioned in the first approach, because of this existence of these arc capacities, it is harder to end up with merges. As such, we end up with relatively larger decision diagrams than the first approach. And we can apply cut strengthening ideas in both. And one last thing is, as a detail, we of course implement these things inside a branch and bound tree and end up with the branch and cut algorithm for these decomposition ideas. And in that algorithm during branch and cut, we also generate pure banders cuts from the LP relaxations of our scenario problems only at integer solutions. In other words, only inside the lazy callback. So finally, we can actually incorporate risk measures into our stochastic programs, and both of these decomposition ideas, they will immediately go through. And why you care about risk measures in general, it's been very, very commonly used in stochastic programming, especially if you are as a decision maker a little bit risk averse, then it's a good idea. And in which applications it makes more sense, which is suitable for our applications, the sensor placement type of application. If you are not making the same set of decisions over and over again in time, but you are making, maybe you are making decisions once and for all and fix them and implement them in reality. So that's why it might be even more important to be risk averse in such decision-making settings. So if you look at the literature, there is this paper by Nilay Noyan who proposed the very first decomposition approach for two-stage stochastic programs where you have this particular risk measure CVAR, where the whole recourse stage is purely continuous. But in our setting, we have actually, remember, binary recourse. That's why there doesn't exist any approach in the literature, the decomposition type of literature for the binary recourse setting. There are some ideas where you have some integer variables in the second stage. They usually end up with a large-scale mixed integer program as a reformulation, which is not easy to solve, I will argue. And also there are some approximation type of ideas. Either, for instance, this MIP is solved by means of a Lagrangian duality, or which will have, of course, a duality gap. And there's another convex approximation. So there doesn't exist an exact method to solve the two-stage stochastic programs with CVAR. And in that regard, our approaches will constitute the first decomposition approach for two-stage stochastic programs with binary recourse and this conditional value at risk type of a risk measure. So again, for the sake of time, I will go very quickly. I will not get into details, but conditional value at risk is a very well-known commonly used risk measure because most and foremost, it has this nice property of being a coherent one. And its definition is implicitly this optimization type of the problem. So it is defined by this single dimensional optimization problem. If you solve this optimization problem, it is optimal objective value will give you the CVAR of your random variable Z. So if we incorporate CVAR into our two-stage stochastic programs, our model now becomes the following. So we do have a component from the, of course, first stage immediate cost, plus as before, the expected second stage cost, plus now for the second stage cost, we also care about the risk of that cost. So we don't want to have, for instance, very, very large values in certain scenarios. We would like to prevent this by being a little bit more risk averse. So what we discussed so far, from which we know how to solve the first part, immediate cost plus the expected cost. Now the idea is how to incorporate the CVAR into this decomposition framework. And I will skip the details, but basically what we end up with is what we were doing before is we were ending up, thanks to our reformulation, these optimality cuts. Now that we have the CVAR, we are also able to end up with a new set of cuts to represent the CVAR value, which is represented for each scenario with this auxiliary variable theta 2. But this is again a slight extension from the literature, this approach by Nilay Noyan, but this is thanks to the simple observation that we have, our whole BDD approach helps us to also employ this for the binary recourse setting. Okay, so now let me show you some small set of experimental results for our dominating set problem, where we are using 1 hour of a time limit, and based on some sample average approximation analysis, we ended up with 850 scenarios for our graphs, and we are considering 200 randomly generated instances who are based on this generation-wise, this deterministic literature for the dominating set problem. We consider up to 50 nodes of graphs with different graph densities, and we repeat for each setting of a node and density, we have 10 different random instances, and we provide the averages. Okay, so what are we going to compare in these computational experiments? We will compare 3 approaches. The standard approach from the literature for pure binary recourse case, for instance, integer L-shaped method, where we are strengthening the integer L-shaped kites, obviously, a little bit, and 2 of our BDD-based decomposition approaches. And we will compare them actually with and without the use of pure Bander's cut from the LP relaxations of our stochastic programs. And this is a simple detail, but it's a game changer because this, for the dominating set, as the results will reveal, the LP relaxation is actually, it turns out to be pretty strong. So these pure Bander's cuts actually close a lot of optimality gap for us, so which was surprising to see. But nevertheless, we want to present the result with and without them. And of course, we will consider with and without CVAR option. So here's where we start without the pure Bander's cuts. If we compare our 3 approaches, the integer L-shape and 2 of our BDD-based decomposition approaches, here we are looking at these performance profiles. On the x-axis, you have the solution time in seconds, and on the y-axis, how many instances you were able to solve by that time. And by the way, this is in logarithmic scale. So basically, if you have a great algorithm, then you would like to see something very close to this top left corner. That would have been a nice ideal algorithm. So if you look at the 3 approaches, then we can see that, of course, integer L-shaped method, this blue curve, it's unfortunately not able to solve many of the instances, more than half of the instances, it is hitting the time limit. So on the other hand, the extension of Leo's work our first BDD approach, it is unfortunately what's happening here is for a significant number of instances, we are hitting our memory limit because the BDDs that we are building, there is not much Merve because of the ARC capacities. We are hitting the memory limit and we cannot build these decision diagrams. For the rest, many of the, again, a significant portion of the instances, if we can build the decision diagrams, actually the cuts are weak from this approach and we cannot solve these instances in our time limit. On the other hand, we consider our second BDD approach where we just built the BDDs with the merges and everything and put the arc cost parameterized by the first stage. We are solving all of our test instances in our time limit of 1 hour. But this is without the pure bandage stats. So now if we turn them on, what happens is actually integer L-shaped is able to actually improve a lot because these pure bandage cuts from the LP relaxation, they are actually closing most of the optimality gap. As such, we are able to now even solve all of the 200 instances with the pure integer L-shaped method. Our approach, the second BDD approach, it is still solving them all, but in terms of here, what we're reporting with the red one, the total solution time, including the BDD construction time, it is doing better here, which are corresponding to instances with higher density. So for higher density graphs, we are actually even with BDDs are costly for us to build because we are building 850 of them. And they are actually still building the integer L-shaped method, but for lower density instances, pure integer L-shaped method is actually much lighter, so it's helping us. On the other hand, if we actually remove the BDD construction time and only focus on the solve time, then we are actually able to beat the integer L-shaped method if we don't have to spend so much time in constructing the BDDs. And finally, I have here one setting where we have the conditional value at risk as an additional component in our objective, and we do have the pure bandage cuts on as well. In this case, under the CVAR setting, despite again the time that we spend on constructing the BDDs and everything, our decomposition approach is doing better than the integer L-shaped method overall. Okay, for the sake of the time, I will just stop here. If you have any questions or any feedback, I will be of course happy to hear. Thank you so much.
Thank you so much, Merve. Are there any questions?
I think one hand is raised.
Margarita has a question. Oh, Margarita just left. I don't have a lot of questions, but I just want to give a...
Yeah, we can talk offline as well. Sorry, I didn't know how long it will take, so I spent more time than I should have.
That's perfect. You have 3 minutes too. 12:15. So first, I was curious also about the multi-stage. Isn't that something, if you have 3 stages, wouldn't you have a sequence of networks? How much more difficult, it seems, how much more difficult it is, for example, 3 stages? Because I wonder what's happening. Yeah, go ahead.
I think this nested bandage thing, ideally it might go through. Although for our second approach, we need to be careful because there's a reformulation there, whether it goes through when you have multiple stages, that needs to be carefully, I guess, thought out. But for the other arc capacity-based approach, I think ideally if you combine the first, I mean, there's also this trick, right? For the third stage now, even if you do the arc capacity version, the capacity should now depend on both the first stage and the second stage decision. So you will have, if you think of the scenario tree model, then for every node of the scenario tree, you need to have a diagram. But ideally, you can still have this nested bandage type of a decomposition algorithm.
Right.
Yeah, that's definitely an interesting direction to think about.
Any questions? Okay, so maybe can I just ask one more question, and then maybe we can go to the break, and maybe just a small clarification question. In your reformulation, when you reformulate network flow, which I think is brilliant, what classes of constraints? I remember that you mentioned the indicator functions and the logic constraints. So what classes of constraints can you actually do that besides? Is that only implications? Can you also do the same thing with nonlinear functions? When does it break that particular formulation?
I think that in terms of this reformulation that we talked about, so it has nothing to do with that, but it's all about like before you come to that point. So if you have some more like nonlinear-ish or more complicated relationships, then here in terms of what my guess is, in terms of the original X variables, you might need to have some other variables. So you need to first figure out how this will look like and then go to the reformulation. But as I mentioned somewhere, I guess early on, in our example, we were lucky enough that we didn't need to introduce any additional variables to formulate such a logic. So we were able to actually directly use from this part our original X decisions and put them as our capacities or our costs. But
Right.
if you have some more complicated logic, you might need to include in your master problem additional variables, maybe one or few more per scenario, and then use those as the capacities. So for instance, if you need to have another for the scenario z of omega, and then you will implement this logic with the help of that variable, these guys, you need to leave them in the master problem, and those are going to be the binary variables passed to the second stage, linking constraints. And through those, you will get the cuts on those additional variables.
Okay.
Yeah.
Got it. Very interesting.
So I think in that side, the dual will have these additional variables, but the reformulation idea will simply go through.
Got it. Got it. Perfect. Okay, so maybe now it's the perfect time for a break. Thank you so much, Merve, for your excellent talk. It was very nice. And then hope to see everybody at 12:30 for our next talk of the day by Leonardo Lozano. And we continue this amazing conference. So let's take a brief break.